In this lesson, we're going to look at the development of the quadratic formula, which is really one of the great results that you're going to encounter this year in math. And before you start this lesson, it's definitely a good idea to make sure you're really comfortable with the method we were using in the last section, completing the square, because otherwise the steps we're going to go through aren't necessarily going to make any sense. And I really want you to understand how this formula is developed, and in class I will ask you to take out a blank piece of paper and do this development. You might want to just simply watch what I'm doing first, and then maybe perhaps you can rewind and take some notes if you like. So we are going to start with a quadratic equation that doesn't have any numbers for coefficients. It just has the coefficients a, b, and c. So we have ax squared plus bx plus c equals 0. And if you go back a couple sections, that's essentially what we started with when we defined a quadratic equation. A quadratic equation is any equation that can be written in the form ax squared plus bx plus c, where a, b, and c are numerical coefficients. So the method we're going to use is completing the square. And the first thing we did when we wanted to solve a quadratic equation by completing the square is we took that last term, the plus c, and we moved it over to the right hand side. So that's what we're going to do now. We have ax squared plus bx, and we're going to subtract c from both sides. Alright, then we divide both sides by a, because we want to have just ax squared on its own. And dividing both sides by a leaves us with x squared. When you divide the bx term by a, you get b over a x, and the right hand side becomes minus c over a. Now here's the completing the square step. So the left hand side has the first two terms of what's going to become a trinomial, which is a perfect square of a binomial. And to figure out what we needed to add to the first two terms, we look at the coefficient on x, which is b over a, and we took half of it, squared it, and added it to both sides. So half of b over a you can just think of as half times b over a, which becomes b over 2a. So b over 2a is what we're going to square and add to both sides. So we have x squared plus b over ax plus b over 2a squared. And we can't just add that to the left hand side, so we'll add it to the right hand side as well. So we'll add b over 2a squared to the right hand side. So now we've completed the square. The left hand side is now a perfect square, and the binomial squared that results is simply x plus b over 2a. The right hand side we're going to need to spend a little bit of time sort of cleaning up. Let's square the b over 2a first. That gives us b squared over 4a squared. And if we're going to add that to minus c over a, it would help if the denominators were the same. So right now we have a denominator of a and a denominator of 4a squared, so we're going to need to multiply the minus c over a by 4a over 4a. And so now the denominators are going to be the same. So on the right hand side, the denominator is going to be 4a squared. Now the numerator we could write as minus 4ac, which is minus c times 4a, plus b squared. But for conventional reasons, we're going to switch those two terms and write the b squared first, and then the minus 4ac second. So we have b squared minus 4ac all over 4a squared. And if you look at what we have now, this was really the goal of the completing the square method. It was to get to the point where you have a binomial squared equal to some number. Now if you think about what the right hand side looks like, a, b, and c are all just numerical coefficients. And so if we're actually using this to solve a particular quadratic equation, we would just have to identify what the values are for a, b, and c. And you can see the right-hand side, b squared minus 4ac all over 4a squared, it's just going to be a number. So this is just going to be x plus a number squared is equal to a number. And what we did at this point was we took the square root of both sides. Now the square root of the left is very easy. We just take away the exponent, so we have x plus b over 2a. The right-hand side, if we take the square root of the right-hand side, remember we have the plus or minus, and the numerator, there's not much we can do with that. We'll write that as the square root of b squared minus 4ac, but the denominator is a perfect square. If you take the square root of 4a squared, you're left with just 2a. And now the final step is just simply to subtract b over 2a from both sides. And initially, we can leave it as two separate terms. And remember, sort of by convention, we always put that before the plus or minus square root term. So we have minus b over 2a plus or minus square root of b squared minus 4ac over 2a. And both of these terms have the same denominator, which is convenient. So we can combine them into a single fraction with the numerator as minus b plus or minus the square root of b squared minus 4ac, and it's all over 2a. This is the quadratic formula, and for all the problems in this chapter, you're going to need this formula. So you might want to have it written on a separate sheet of paper so that you can use it to tackle all the problems that we're going to look at. With some time, I hope that it will become second nature to you and that you'll have it memorized. And I think also the practice that you will devote to being able to develop this, to go through the steps I just went through, will also help you memorize it. I think it's very, very valuable to be able to know where formulas come from. It's not always possible. Some of the formulas you use in high school math you actually need calculus for, things like the volume and surface area of a sphere. But where possible, it's nice to know where these formulas come from, and then they're not just simply black boxes. They are truly time-saving methods. Right? You could use the whole completing the square method to solve any quadratic equation, but it's faster to use the quadratic formula, which is really just an encapsulation of that method that you already know. So let's see how you're going to use this formula now to solve quadratic equations. And we'll start with a couple of quadratic equations that can be factored, which means that they will give us rational roots. And they're also easy to check by factoring. So the first example is a very straightforward quadratic equation, x squared minus 5x plus 6 equals 0. And we know we can factor this quite easily, x minus 2, x minus 3, which would lead to the roots 2 and 3. So let's see if the quadratic formula gives us the same roots. The first thing when you're going to use the quadratic formula to tackle a quadratic equation is you have to make sure you've got everything on one side and 0 on the other side. That's already the way it's written. And then you need to identify the a, b, and c. In other words, the coefficients on x squared, x, and the constant term. So the coefficient on x squared is just 1. The coefficient on x is minus 5. And the coefficient, the last term, the constant term, is 6. So we can go ahead and apply the quadratic formula. X is equal to minus b. Well, since b is negative, minus b becomes positive 5. Plus or minus the square root of b squared. So regardless of whether b is negative or positive, this is always going to be a positive number because you're squaring it, so you get 25. Minus 4 times 1 times 6. So 4 times 6 is 24. And this is all over 2 times a, which is 2 times 1. So let's simplify this. This is 5 plus or minus 25 minus 24 is 1. And the square root of 1 is just 1. So this is 5 plus or minus 1 over 2. And since this is a rational, there's no radical involved, we can simplify this quite easily. We can write this as x equal to 5 minus 1 over 2, or 5 plus 1 over 2. And these are the expected roots that we can get by factoring as well, 2 and 3. Very nice. Let's try a slightly more difficult one, but one that can still be factored. So we'll take a look at quadratic equation 3x squared plus 5x minus 2. And if you were going to try to factor this, you would be looking for two numbers with a product of negative 6 and a sum of 5. And since you can find those two numbers, positive 6 and negative 1, you know this can be factored. And you can do that separately if you want to verify what the roots are. But again, make sure everything's on one side, which it already is. Identify the three coefficients, a, b, and c. In this case, a is 3, b is 5, and c is negative 2. And then go ahead and apply the quadratic formula. So x is equal to negative b. In this case, b is positive, so negative b becomes negative 5, plus or minus the square root of b squared, so that's 25 again, minus 4 times 3 times negative 2. So since you're multiplying this by negative 2, you can change the sign on the minus to make it a plus. And this is all over 2a, 2 times 3, which is 6. So in the radical, we have 25 plus 4 times 3 times 2, which is 24. 25 plus 24 is 49. So it is minus 5 plus or minus root 49 all over 6, and root 49 is an integer, 7. So we have minus 5 plus or minus 7 all over 6. So again, because it's rational, there's no radicals floating around, we can simplify this quite easily. The two roots are minus 5 minus 7, that's minus 12 over 6, or minus 5 plus 7, which is 2 over 6, and those can be simplified as negative 2 or 1/3. And you can verify by factoring that those are indeed the two rational roots to this quadratic equation. All right, so let's move on to a couple of more quadratic equations, this time that can't be factored and that don't lead to rational roots. So example 3 is 2x squared minus 7x plus 1 equal to 0. And you know this one can't be factored because there are no two numbers that have a product of 2 and a sum of negative 7. So again, I've got everything on one side. If I didn't have everything on one side, I would want to move everything to one side. So we have a, b, and c. We need to identify. A is 2, b is negative 7, and c is 1. And we can just go ahead and apply the quadratic formula. X is equal to negative b. Since b is negative, this is positive 7, plus or minus the square root of b squared, that's 49, minus 4ac, so 4 times 2 times 1, all over 2a, which is 2 times 2, or 4. And inside the radical, we get 49 minus 8, which is 41. So we have 7 plus or minus root 41 all over 4, and there's nothing we can do there. Now, if you can simplify the radical, in other words, change it into a mixed radical, for instance, root 20 you would write as 2 root 5, then you need to do that, and then there may be a common factor of 2 that you can pull out. In this case, there's nothing you can do with root 41, and that's the final way you would write the answer. Now, if you want to figure out what the decimal approximations of these are, you can plug them into the calculator. We can get a rough estimate of it because we know that root 41 is a little bigger than 6 and smaller than 7. So 7 minus root 41 is going to be close to 0. And certainly when we divide it by 4, it'll be even closer to 0. And then, but it'll be positive. And then 7 plus root 41 is going to be a little bigger than 13, smaller than 14. And when you divide that by 4, you're going to get a number somewhere between 3 and 4. All right, finally, let's take a look at a word problem, which leads to a very famous result. So here's the word problem. What positive number is one more than its reciprocal? Okay, so the most challenging part of this might be just writing the equation. What positive number, right, we're looking for some number, we'll give it a variable, x, translates as equals 1 more than its reciprocal. Well, its reciprocal would be just 1 over x, and 1 more than that would be plus 1. And we'll just put a little x greater than 0 here to remind us that we're looking for a positive number. Okay, so at first this doesn't look like a quadratic equation. There's no x squared floating around. But because it has a fraction in it, the first thing we would like to do is multiply both sides by x to clear the fractions. So if I multiply the left side by x and the right-hand side by x, the left-hand side becomes x squared. The right-hand side becomes 1 over x times x, which is just 1, and 1 times x, which is x. And so now we can see this is indeed a quadratic equation. And again, the first thing is to get everything over to one side. We'd like to get it onto the side that has a positive coefficient for x squared. So in other words, we'll collect everything on the left. So x squared minus x minus 1 equal to 0. And now let's apply the quadratic equation. So we need to identify a, b, and c. So the three coefficients are 1 is the coefficient on x squared, negative 1 is the coefficient on x, and negative 1 is the constant term. So when we apply the quadratic formula, we get x equal to negative b, which ends up being positive 1, plus or minus the square root of b squared, that's just 1, minus 4 times 1 times negative 1. So since we're subtracting a negative, we're actually going to be adding 4 here. And this is all over 2 times a, or 2 times 1. And so there isn't much simplification to do here. We just have to add the 1 and the 4 in the radicand and get 1 plus or minus root 5 over 2. Now, there are 2 roots here. And since root 5 is a little bigger than 2, 1 minus root 5 is going to be a negative number. So since we're looking for just the positive number, our answer to this is simply 1 plus root 5 over 2. And this is pretty common when you're using quadratic equations to solve word problems. You will almost always get 2 roots, and sometimes both roots will be valid, and sometimes one root will not be valid based on the original word problem, and you'll just toss one out or ignore it. It's not to say that the 1 minus root 5 is not a solution to the quadratic equation, but it just doesn't satisfy the conditions of the original problem. Now, this number is, as I said, a very special number or a very special result. This is the golden ratio, and the golden ratio pops up in math all over the place, and it pops up in mysticism and ancient Greek mathematics. The golden ratio is considered the sort of ideal ratio of length to width for a paper, and there's a very nice number file video that I'll post on the website that talks about having paper designed in this special ratio. Let's just stop for a second though to verify that this number truly is 1 more than its reciprocal. So as I said, this is called the golden ratio, and the golden ratio is symbolized with the Greek letter phi. So we'll write it as phi is equal to 1 plus root 5 over 2. And the reciprocal of phi would therefore be 2 over 1 plus root 5. And let's just see what the decimal approximations of these are. Punch it into your calculator. You'll see that phi is 1.618033989, etc. It goes on forever. And the reciprocal is 0.618033989, etc. So please make sure that you memorize the quadratic formula. It'll become second nature the more you use it to solve problems. And also make sure you can develop the quadratic formula just starting with ax squared plus bx plus c. I believe it's really important to be able to develop these formulas where possible on your own, so that they're not just sort of mysterious black boxes, but you actually know where they come from and can see them as just simply time-saving encapsulations of methods that you already know how to do.